evaporated, but I'm going to try to hold on to the feeling just a little bit longer. Anyway, so let's just get started with the organization. Things are going to be similarly organized to Quantum Optics 1. As before, all the material will be distributed through the course website. I'll email you the link, but it's also available on the Physics and Astronomy Department schedule page. So all the materials will be distributed here. We have two TAs helping us again, this time Paulo and Mosin, and they'll be sharing the duties of office hours and grading. Right, so let's see. Again, there are no texts that are required for the course, but there are some recommended texts, and I guess I have some of them listed down below here. I do recommend getting some other texts. I mean, you know, there's just one voice you're hearing otherwise, and there's other perspectives. It's good to have some, you know, additional perspectives and voices. So they're available in various forms. I'm just particularly picky in how I like things organized, and so I never followed the textbook for any course over time. Right. So let's see. The materials, or to say the topics that we will address are partially a continuation of what we were discussing last semester in our study of non-classical light and different ways that we characterize classical versus non-classical light. We'll review that today in today's lecture. But that will open up us to other parts of the discussion, including some applications and foundations of quantum mechanics, like the notions of entanglement and CPTP maps. Open quantum systems is going to be a big aspect of what we discuss this semester. You know, as I sort of said in the past, quantum optics has kind of been the forum, has kind of been the sub-discipline of physics in which the sort of foundations of quantum mechanics have been explored most deeply, and how the questions about the shut up and calculate mentality was kind of rejected by quantum opticians. That's why we became quantum opticians in the 1980s. It's because those are the questions we didn't want to shut up and calculate and we're interested in. Now, of course, they've become the foundations of what we understand in quantum information science. So many quantum opticians became quantum information scientists, and that's sort of my life story. And so we'll talk a lot about that this semester, and I hope we'll talk about some applications as well in some of these areas. Right, okay, so the grading will be as such. 75% will be homework, problem sets, and 25% will be a final project. The homeworks, well, there'll be 5 assignments, not 8. And they're going to be over a period of 2 weeks so that you have to be more organized. Because if you wait till the last minute, you are going to be sorry. I promise you.
I know. I was sorry last semester too.
Okay, so more sorry.
It'll be
So,
even more
yeah.
sorry.
No, you know,
Twice as
I am an expert procrastinator. I perfected it. I have a terrible sense of space, but I have an awesome sense of time. And you just have to know how long it's going to take to do something. You could push it off, but don't push it off until that point where you know it's going to take that. That's your deadline. Okay, that's how you procrastinate. You procrastinate until you hit the time you know how long it's going to take. You don't take more time, then you waste time. So if you procrastinate till the time you know it takes, then you're going to take exactly how much time it takes to do the thing. That's my strategy. Okay, so if you're going to procrastinate, know how long it's going to take, and don't go past that deadline. All right. All right. What else is there to say in the overall? So this is the syllabus, and you know, I think we'll cover this this semester in various forms. These applications will occur more in the context of this homework than in the lectures. Okay, and as before, there will be posted lecture notes, and there will be links to the recorded lectures that will be posted on our YouTube channel. Okay, and so if you give it lots of hits, then we'll get lots of ads, and that'll be terrible. So you know, watch it. Spare. Okay, so the assignments, the first assignment I will distribute next week. Okay, so there won't be any more. Does anybody have any questions? Okie dokie then. Let's power off. Yes, I mean it. And let's just get started. Okay. So, what I want to do today is review what some of the things we talked about last semester and think about the big picture context of what we discussed so that we can use that as a launching point for further discussions. And as we discussed, the subject of quantum optics is intimately related to the subject of quantum coherence. Okay. Quantum coherence is, in some sense, you might say, the secret sauce that gives quantum mechanics its magic powers. What we mean by quantum coherence and the way that it manifests itself are some of the questions we want to ask ourselves. But we're going to talk, you know, throughout this semester of different ways that the secret sauce manifests itself. Okay, but quantum coherence, of course, is intimately related to the notion of interference. And as we discussed, well, interference, if we think about it, we have the classical wave interference. That is to say, when we have vibrations of something that satisfy some kind of linear response, we can have interference between those oscillations, as in the electromagnetic wave, right? Whereas if we think about quantum interference, what we're talking about is the probability amplitude for predicting measurement outcomes. Okay. So fundamentally, quantum mechanics all we got. All quantum mechanics does is allows us to somehow assign a probability to what we're going to measure, or what the probability for a particular outcome will be in a particular measurement, okay? And the prediction of those outcomes can exhibit the properties of quantum interference. Now, these two things come together if we're thinking about quantum optics, when we're thinking about the quantized electromagnetic field. In the following senses, okay? So the things that we're interested in asking ourselves as we have is the notion of classical versus non-classical. Under what conditions do we need to quantize the field? And in what situations can we get away with the classical description of the field, and the interference phenomena that we see are associated with those? Now, to the degree that we believe, and that degree is 100% right now, that the fundamental theory is quantum mechanical, then there's an aspect of this that we'd like to understand, which is how do we recover the classical description from a fundamentally quantum description? So the issue of the classical limit has been an important aspect of what we have studied and what we'll continue to study. And another aspect of this is not just cataloging or being able to put into boxes, is this classical or is this non-classical, but we'd like to understand something about the power of non-classicality. That is to say, you know, what can we do with non-classical phenomena that we couldn't do if the world was restricted to the classical description? So that's the envelope in which all of what we're doing lie. So let's just remind ourselves of some of these things and what we discussed last semester. When we think about classical wave interference, we thought, for example, of an interferometer. And the interferometer is something which allows us to see interference between two different, for example, paths of waves, right? So this is our Mach-Zehnder interferometer. It's our sort of fruit fly of interferometers. And we are typically, what we're doing is we're measuring the intensity at the output port of one of the interferometers or another. And the intensity that we see at this output port is, for example, the time average of the square of the electric field at the output port. Okay, with some constants, depending on what units we're looking at. And you know, to the degree to which we said that this system was ergodic, then we can think about this in terms of a statistical average. So this is the time average. And this is a statistical average, say, at any time, because if it's a statistical average, it's stationary and ergodic. So under that condition of stationarity, of the statistics, then we were able to replace a time average by an ensemble average, right? So in this case, this output field is a superposition of the fields that arrive at this port through these two different paths. And so the electric field in this case, we have for a 50-50 beam splitter, where T1 and T2 are the two retarded times associated with the path lengths L1 and L2, right? And we remember that we can write this field in terms of the positive and negative frequency components, which represent all of the frequency components with positive frequencies from 0, so this is the integral from 0 to infinity d omega of the Fourier transform of the field. That's E plus, and E minus goes from minus infinity to 0, and they represent the complex conjugates of one another. They are related to the positive frequency component is related to what we call the complex amplitude by twice the complex amplitude, where the electric field is the real part of the complex amplitude, which is 1/2 that plus that star, right? So we have these relations to the positive and negative frequency components, complex amplitudes, et cetera, et cetera. And so our output electric field over here, this time average was the square of the complex amplitude, which I could write as E minus times E plus, which is equal to 1/4 E n t minus T1 or I just write it in terms of the complex amplitude. It doesn't really matter. There's factors of 2, but I'm not going to keep track of them. So I'll write it like this. And for a stationary field, this is 1/2 times the incident input intensity plus twice the real part of the, I should write the correlation function here, of E in T1 minus T2, E in at 0. Okay, everyone, so far so good? Any questions so far? Just getting our brains restarted and thinking about this stuff again. And so this, one of these guys should be starred. This we call the correlation function G1 at T1 minus T2. And if we factor this out, this is 1/2 the input intensity times 1 plus little g1 at T1 minus T2, where little g1 is equal to big G1 divided by the intensity. So for example, in this Mach-Zehnder interferometer, if we plot this intensity at the output as a function of this, what we found, for example, we might see something that looks like this. This might be the interference pattern for, e.g., thermal light. With bandwidth delta omega, where this falls off with some coherence time that's inversely related to the bandwidth, and there might be some carrier frequency. And this represented for us the coherence time. And we understood this interference and the loss of coherence just in terms of the fact that the phase of the wave was not well defined, that it was disturbed, for example, due to collisions between the particles, and random waves led us to understand from a statistical wave theory. So we had this understood in terms of random wave amplitudes. Okay. So what about from the quantum perspective? Well, firstly, we have the notion of the quantum state. Which generally we said was represented by a density operator. And what we have that in quantum mechanics is the rule that tells us how to assign a probability to a measurement outcome, which is the Born rule. And the Born rule tells us that if I have a measurement, then the most general measurement is described by a POVM. And a POVM is a set of operators, could be a continuous uncountable set, or a countable set of operators, which I'm calling E, which are a resolution of the identity. And the probability of finding outcome A is the trace of rho with the POVM element. So this is just jargon. The elements of the POVM are positive operators. There are operators whose expectation values are positive numbers, which means they could be probabilities, and they're normalized in this way, in that so any set of positive operators forms a potential measurement in principle that could be done on the system. Now, as we remember, the sort of usual measurement are of observables. This is the language we typically first learn when we learn quantum mechanics, the observables being permission operators which might have will have a spectral decomposition in terms of eigenvalues and eigenvectors, and the probability of finding this is some projector onto that outcome, that is to say, when you multiply it by itself, you get it back, and that forms a POVM, that's to say, a resolution of the identity. We're all familiar with how you deal with quantum mechanics. You always shove in a resolution of the identity. It's always the first thing to do. And it tells us that for observables, what we're really doing is measuring in a basis. Okay, so the projector is the set A is a basis for the Hilbert space, and the probability of seeing eigenvalue A, which is really one of the basis elements, the trace of rho with the projector, which is the POVM element, which is that, which is the diagonal element of the density operator, or the density matrix, gives us the probability. So the diagonal elements of the density operator give us those probabilities. And if this is a pure state, so rho, for a pure state, rho, we remember itself is a projector. It's a projector onto a particular vector in Hilbert space, which we call the state of the system. For a mixed state can always be thought of as an ensemble of possible pure states. Those ensemble, as we know, need not be, there's not a unique ensemble that gives the same, that gives rho. There are many different, we studied that last semester as well. Right, so quantum coherence. If we have let's say we have a pure state psi, which itself is a superposition we write in terms of two other states, say U1 and U2. Let's say that these guys are orthogonal, or doesn't really matter, let's just suppose this is true. Okay, and now we ask ourselves, what is the probability of seeing outcome A in a projective measurement, for example? So for this particular case, well, this guy for a pure state is that's to say it's the square of the amplitude. So all of these things, this is what we learn. It's kind of going backwards the other way. The probability of seeing the outcome is the square of the probability amplitude, which we can think about in terms of this picture as a diagonal matrix element of the density operator, which is really the Born rule with the POVM element, which is a more general thing, right? So we should kind of try to ensure we connect all those different descriptions of really the same thing in different generalizations. In this particular case, for the pure state, if my state is of this form, maybe let's go to a new board. So when the state, let's say, was a superposition of these two states, then the probability of seeing A, we say, of course, is the square of the amplitude, which is the square of this amplitude, which is C1 squared amplitude squared times C1 squared plus this amplitude squared times C2 squared plus twice the real part of C1, C2 star, A, U1, U2, A. Right? Which has a similar flavor to what we saw over here in the interference of the classical waves. In this context, though, what these amplitudes represent is not the strength of a vibration of anything, but it represents something related to the probability of the measurement outcome, okay? And this is the probability of finding A given that the state was U1 times the probability that it was U1, right? This is a conditional probability. Plus the probability of getting A given that the state was U2 times the probability that it was in U2, which is this amplitude squared, plus something that isn't the probability of anything, but is the interference term. So what it tells us, of course, is that the logical prediction of what we're going to see in a measurement can't be argued logically, because this is logic. These first two terms is what you would expect if there were two possible alternatives, U1 and U2, that it could have happened in this system, because those were the only two alternatives in this orthogonal state. We would use Bayes' rule to predict this probability, but this says Bayes' rule doesn't work. It's illogical. Okay? That's life. So, again, we want to connect, we want to remind ourselves the connection between these two pictures. How does this picture, particularly in the context of the quantized electromagnetic field, how does this picture of interference of what we think about as the classical wave, which is the vibration of the ether, if we want to call it that, or whatever the electric field, how we want to think about it, and this picture of interference of amplitudes of what? And how do these pictures connect to one another? And how, in what context, are they different from one another and not describable by one another? So for that, I want to remind ourselves in one quick line about the quantization of the electromagnetic field. Okay, so the way in which we quantize the field was to think about it in terms of normal modes. And then to decompose the field to normal modes, each mode of vibration is a harmonic oscillator, and so we just quantize the harmonic oscillator associated with each of those modes. We might label them with a generic index I'll call K, which might include the polarization or the momentum or what have you, okay? And just loosely, what we then would say is that, okay, the positive frequency component of the field is now quantized by decomposing it into these normal modes with amplitudes that are now the creation or annihilation operators. For the positive frequency component, they are the, and then we might have some units, characteristic scales. Like the square root of h bar omega over the volume is the strength of the electric field in the right units. So what's important here is that what we have is these commutation relations equal time, typically commutation relations the A's all commute with themselves, the A daggers all commute with themselves, but the A's and A daggers for the same mode don't commute. And these are the Bose commutation relations. They're the Bose commutation relations because these guys commute. Because they commute, you can, when you exchange particles, you get the positive sign for the exchange symmetry. So the reason, of course, the electromagnetic field is a boson is intimately related to the spin statistics relations. Photons are spin 1 particles, therefore they're bosons, but they're kind of crazy spin 1 particles because they're massless, and because of that, they don't have, they only have well-defined projection of spin angular momentum along their direction of propagation, along their momentum. So we only have two, we don't have a transverse, we only have, with that we have a transverse field, okay? Okay, and then this also told us that we have Fock space, Fock with an F, not a PH. Which is the Hilbert space associated with the quantized field, which is the Bose space, which has some number of excitations. This is really a tensor product in some modes. So this is a basis of the Fock space. These are sometimes called Fock states. I hate that name because everything in Fock space should be a Fock state, but you know, the ones with number, this really should be called number states, but everyone calls them Fock states. But everything's a Fock state because of the Fock space, but anyway. You know, you missed me, didn't you? Miss a diatribe. I have to complain about something. All right. Right, so importantly, the quantum field theory has the notion of particles. And the particles are quanta of excitations. Okay, so we can have a state of the field that has a definite number of quanta. Those are the Fock states or the number states. They don't have to be in any one of the modes. They can be in a superposition of those modes. So for example, I can have a state, a 1 photon state in some wave packet, which I would write as a superposition like that. This state is an eigenstate of the number operator. Do you see that? So this is a single photon state. number operator is the sum of the number operators in each mode, which is A dagger A for that mode. And the state that I'm calling 1 comma psi, so if I write, so I'm going to let psi be sum over ck uk in first quantization. This would say I have a particle that is in a superposition of some basis states. This might be a particle in a box, and this would be, say, the superposition of the energy eigenstates. Okay? In second quantization, we wrote it like this. This is one, in this case, photon in the mode K. So this is two notations for the same thing. The second quantization is a way of us allowing ourselves to deal with the many-body structure. The fact that there are particles and there can be more than one is that there's an intimate relationship between quantum field theory and many-body physics, which is why condensed matter physicists borrow a lot from quantum field theory because of the intimate relationship between the physics of many bodies, particularly many identical particles like fermions or bosons or anyons, and the quantum field description. So this state is an eigenstate of the number operator. Oh, this would be 1 sub psi, excuse me. I caught my mistake there. I can also write this as creating a particle in the wave packet psi, where this operator is just a superposition of those creation operators. Okay, so this operator creates 1 photon in the wave packet psi, and this is an eigenstate. So if I write this with 1, this has the eigenvalue 1. Okay, so it's a 1 photon state. So the particles are the quanta of excitation of the system. There's the notion of waves as well. And so we'll come to that and remind ourselves about that in a moment. Okay? Our goal is to remind ourselves now of how we think about this problem where we have something like an interferometer and a detector from the quantum perspective, and how to relate what this description is in terms of the quantum field is into the classical description and their interrelationship between them. So for that purpose, let's remind ourselves of the Glauber theory. And the main point here is that if I have a square law detector, which counts photons, the square law detector is the quantum analog of what we had of our detector that measures the intensity of the field, that if we use the full quantum theory in quantizing the field and the matter, that what we find is that the intensity operator that we would find at some position in some time is the same type of field that the same sort of expression we saw in the classical case, but now with the quantum field. And in particular, it's in so-called normal order. And the normal order is, and for the moment I'm ignoring the vector nature of the field. Mostly I'll do that. For some mode has the positive frequency components to the right. These are things associated with the annihilation operator. And this is the things associated with the creation operator. Okay, and that came out of thinking about Fermi's golden rule in the way in which photons are detected. Okay, so let's suppose that the state of the system was, let's suppose that I have my Mach-Zehnder interferometer, and I send in a single photon wave packet into this interferometer. Okay. By the way, for this single photon wave packet, what is the expected value of the electric field? What's the mean electric field associated with this state?
Electric field goes essentially as an annihilation operator.
So this will have either a annihilation operator or a creation operator, which will either annihilate or create a photon from this mode. And then I look at that, which is orthogonal. So the answer is 0. So there is no mean field. So this is in no way like what we might think about. It's a very, in some sense, non-classical state. Nonetheless, if I ask about what is this expectation value, which is related to this sort of mean photon counting, and I ask that question, what is the answer to that? So if I look at the intensity of this guy, what is that? Well, there's one trick I can play in this context. Since this guy annihilates a photon from this, I can shove in a complete set, and the only thing that's going to remain is the vacuum. Because anything that had different number of photons will be orthogonal to this. Okay? So this is equal to the square of that. Because this is the complex conjugate of this. Does everyone see that? And this, when you plug in this and you do a little bit of work, you'll see is equal to that. where these are the mode functions associated with each of the modes, which is just what we would call the wave function of the photon. It's psi star psi, which we learned about in sophomore physics. So the second quantized theory gives us the same thing as we learned in sort of basic wave mechanics, which is that if I want to see what's the probability of finding the particle somewhere, I square the amplitude of the wave function that tells me the amplitude for finding the photon there. Okay? So in this particular case, psi at r out at t is equal to the same kind of expression we saw for the classical electric field. It satisfies the same superposition of two possible paths with the beam splitter transformation. And when I look at the square of the amplitude, I'm going to see the same interference that I saw from the classical waves, now expressed in terms of the wave function of the photon. In some sense, the wave function is like the electric field, but it's confusing, right? I mean, what I just said was this object is the wave function of the photon. But it's not the mean electric field of the photon. We just said the mean electric field of the photon is 0. But mathematically, the amplitude that we see is proportional to that classical electric field. We need to kind of put all that together. Okay, I'm going to think about it. I'm not crazy. I'm just trying to say this is all wrapped together. It's well, maybe I'm crazy. You can decide that. I can't. I wouldn't be able to decide and tell you. Okay, so from that point of view, what we need to remind ourselves is the notion of what we mean by a classical state of the field, of the quantized electromagnetic field. What is the quasi-classical states are Glauber's coherent states. Okay, so for a single mode, call that state alpha, this state is defined as an eigenstate of the annihilation operator. If I have a multimode I might write them like that, where I have an eigenvalue for each of the modes. And then, as we've seen, this is an eigenvector of the electric field of the positive frequency component. I hate whiteboards. Not that my handwriting is that much better with chalk, but I felt I had a little control. Where this is just the classical field. with that decomposition in terms of normal modes with these amplitudes. So, in fact, for a coherent state, the electric field has the mean field, which is the classical field. So this has exactly the right classical mean field. It also is, I won't go through that, is minimum uncertainty product. We'll come back to that more next lecture. We remind ourselves more about the continuous variable aspects of this. This can't be a state with a definite number of photons, because we just said a state that's a Fock state has zero mean field. So there is this relationship, this uncertainty between knowing something has a well-defined phase and a well-defined number. There's the phase number uncertainty principle that we talked about. The coherent state, as we remember, is a superposition of Fock states or number states with particular amplitudes. And this state, the coherent state, has a mean number of photons, which is the square of the amplitude, and a fluctuation, a variance, or RMS, which is the square root of the mean. So this state doesn't have a definite number of photons. It has this particular superposition in such a way that it has this mean field. The probability distribution of seeing n photons, the square of the amplitude, is, of course, we remember, the Poisson distribution. Which has this kind of variance. The Poisson distribution has this kind of variance. So, the coherent states are what we call the quasi-classical states. They are the states that are the states of the quantum field that are closest to the classical electromagnetic field. They satisfy the properties that they're radiated by a well-defined classical current. If we treat the current as a classical current and we quantize the field, then the state that arises from the quantum theory is our coherent states, if that current is deterministic and has a well-defined oscillation or time dependence. If the current, as in the current flowing through these light bulbs, is random and stochastic and we don't know what the current is, then we have a statistical mixture of coherent states. So what we call classical light is a statistical mixture of coherent states. Where P is a function which is greater than or equal to 0, which is the so-called Glauber-Sudarshan P representation. As we'll see, there are multiple representations, and their implications are important for our understanding of distinction between classical and non-classical light. For now, this is how we're distinguishing classical versus non-classical light. If the state has this form that constrains in some way the statistics of the problem. So let's just consider for a single mode. If I ask what's the probability of finding n photons in the mode, that's that, which is that, which is a statistical mixture of different Poisson distributions with different amplitudes and different mean numbers of photons. So what this tells us in this situation is for classical light that the fluctuations in the number of photons is always bigger than or equal to the mean number of photons. It's only when this is a delta function, where we have a definite amplitude, that we have the minimum fluctuations. There will be additional fluctuations in the number of photons that we'll see if we measure in a given time interval or in a given mode, that will in general be due to the fact that there are intensity fluctuations. Okay, so what we remember, so we have for a coherent state, the probability of seeing n photons is the Poisson distribution, and the mean number of photons is the square of the amplitude, and the Glauber distribution, let's say alpha naught, is a delta function. We have that definite amplitude. So this is the coherent state. In contrast, if we have a thermal state, where rho, for a given mode, is given by the Boltzmann distribution, then we remember that the probability of finding n photons in the mode is what? Something n bar to the n over 1 plus n bar to the n plus 1, which we call the Bose-Einstein distribution. Right? We can get that by just looking at the diagonal matrix elements of the density matrix and playing some games as we did in homework with some pain or not. What is the P representation, or what is the distribution of amplitude associated with the thermal state? What is its form? Well, it's not a delta function. It's not doesn't have a definite complex amplitude. It's a thermal state. You know, remember, what is the form? It's a Gaussian. Yeah. All right. And so it's a Gaussian centered at the origin with a variance that is the mean number. Okay. And in this case, for the coherent state, the fluctuations in n are the square root of n, or equivalently, the variance is equal to n. In this case, for the thermal state, the variance is what? Well, it has to be at least n bar, because it can't be, it's always bigger than that. And how would we find that? Well, that's equal to the mean of n squared minus the mean of n squared, okay? The mean of n squared is the mean of A dagger A times A dagger A. Now, if we have the Glauber-Sudarshan P representation, when we calculate expectation values, the best way to do that is to commute things and put them into normal order. So I'm going to commute this to put the A dagger on the left and the A on the right. So that is equal to A dagger times A dagger A plus the commutator, which is 1. Everyone see that? So that's the mean n. Okay? What about this? Well, this is equal to the integral over alpha, P of alpha, everyone see that? Which is equal to alpha squared, alpha star squared, which is alpha squared squared, or alpha to the 4th. So this is equal to the statistical average of the intensity squared, or alpha to the 4th. So the fluctuation in the number of photons in the mode is equal to n squared minus the mean n squared. The mean n squared is that squared. Everyone see that that's the mean n? Right? Which is the average of squared. We put this all together and we see the following, that the fluctuation in the number of photons in the mode is equal to n bar plus the mean of alpha to the 4th minus the mean of alpha squared squared. which is equal to n bar plus the fluctuation in the intensity. So for a coherent state, you have the minimum, which is just due to the corpuscular nature, the discrete nature of the quanta in the field, and the fact that there is an uncertain number of quanta in the field. But if you have classical light, there can be excess fluctuations coming from this. For a thermal state, this is equal to n squared. Okay, so for a Bose-Einstein distribution, and Einstein kind of noticed this when he looked at the, and he's, as history tells me, I never met him, is that, you know, there's a piece that's kind of the wave piece and a piece that's the particle piece that is associated with the Bose-Einstein distribution. So what we have, one of the signatures of classical light is that we can have, or the classical light is super Poissonian statistics. It could be Poisson as well, but it can never be less than, the fluctuations, the variance can never be less than that. If it's less than that, if we have sub-Poissonian statistics, then that is something that can't be considered as arising from a classical current that was fluctuating in some way. It has to come from a non-classical source. And so that's one of the other things we want to discuss about this semester is non-classical sources of light. All right, I think I'm going to stop a little bit early because I don't want to go over where. The next thing we want to talk about, so maybe I'll just say just a few more words to conclude, remind where we're going. So what we've seen. Oh, maybe I'll say one more thing. I can't. There is time for one last thing, but I want to add it. So let me do that. This is a crappy eraser. Or I write with a heavy hand.
You can still see the electrodynamics.
Okay, well there you go.
I think that shows it.
I should bring my own Windex or something. If we look at, as we said, the intensity, if I have a coherent state, that would be equal to right? This is an eigenvector of E plus with the eigenvalue of the classical field, and this is its complex conjugate, which is just equal to the mean number of photons times the square of the wave function of a single photon. From exactly what we wrote down over there. So we can think about what we're seeing when we see, if we send in, say, a laser interferometer, we can think about it as each photon interfering with itself. That's to say, going through, there's an amplitude for it to go one way or the other, and every photon has some two different histories that can lead to the final outcome. We don't know which of those histories it went, so we have to add the amplitudes for those histories and then square them. And that, so even though we might see more than one photon, and each photon is undergoing its own interference. We don't know how many photons we have, but if we looked at this particular, we did this expectation value, we would find this intensity, which is just given by the mean number of photons. And this is a photon by photon interference. Even though there are many photons, this captures Dirac's statement that every photon only interferes with itself. But that's only true because we're only looking at a single detector. So what will distinguish the classical from the non-classical light is not these kinds of interference experiments, but the photon correlations, the many-body correlations or statistics between those photons are what's going to distinguish the classical light from the non-classical light. And that's what we'll remind ourselves some more about in the next lecture, and then we'll go on to some of the newer material. All right. That was a breezy way back into the semester.